I should have a clapboard.
Tim, are you good? Would you give me the sign?
Yep. Ready when you are.
Okay, well, we've got a full house here at Topos Institute. We've got people here, and we're very delighted to have Bob Harper. But first, we'll have Ilyas Khan, our Topos Institute chairman, give a few words, and then we'll move to Bob. So please, Ilyas.
Well, thank you, David. Thank you, Brendan. Thank you, everybody. Thank you, Bob, for coming along today. Look, I just wanted to make 2 or 3 points because I think occasions like this are a way of aligning 2 aspects of the Topos Institute. There is the scientific and mathematical research work which is going on, but there's also a broader perspective, and it is that perspective that aligns me with you here today, but particularly with David and with Brendan. So what I wanted to do was really take a step back, and in the 2 minutes that I've got, I wanted to remind us of what it says on the Topos Institute website. It says that we shape technology for public benefit by advancing sciences of connection and integration. And our goal is a world where the systems that surround us benefit us all. There's more on the website, but those are the key points that I think summarize the mission of the Institute. Now, in my day job, I'm very privileged. I'm the chief executive and the founder of a quantum computing business that has grown to be the world's largest and most important quantum computing company. And things will change because of quantum technologies. When I first met David and Brendan, I was inspired by their vision that actually we can make a difference. I mean, so often people just shrug their shoulders in the face of this enormous inequality and iniquity that exists when technology is untrammeled. I have children. My children might end up being victims of some of the worst aspects of what this world has in store for them. I know that here we're talking about research, but the Topos Institute exists for a broader purpose, and I'm really optimistic, inspired, and very privileged to be able to support David and Brendan. Their vision got me out of bed and helped create this institute, which I think will be a force for good. So as we focus now on the Colloquium and Bob, and as we have done in other research meetings, I think if we can take a second to remember why the Institute exists and the very real challenge that we have to try and influence the world around us and to show them that there is a different and better way of embracing change whilst at the same time being accountable, then my children's generation might actually not have to face the kind of horrid environment that we faced growing up. I'm going to hand over back now, I think, to David or Brendan, who will hand back over, I guess, to Bob. But thank you for giving me the chance to say this few minutes and take this time. Okay.
Thanks so much, Ilyas. Great, thank you so much. So now we'll move to Bob Harper. So Bob, would you share your screen when you get a chance? And
yep, or I'll give this a try.
Great.
Okay. Is that visible?
Yes. So
okay, good.
Yeah, we're very
Can't
pleased
believe
to have
the trouble. No.
Very pleased to have you here, Bob, talking about phase distinctions in type theory. So please, floor is yours.
Are we good?
Yep, whenever you're ready.
Oh, okay, sorry. Okay, so I guess I'll get started. So I guess first of all, I wanted to thank David and Tim for the invitation. It's an opportunity for me to share some ideas that we've been working on in my group. Oh, and I should say, going back to my first slide, so the work I'm presenting is joint work with my now colleague, former student, John Sterling, who's at Aarhus now, Yuan Yu, who's a student, my PhD student at CMU, and Harrison Groden, who's undergraduate student working with me at CMU at the moment. And the bulk of the things I will talk about is work I'm doing jointly with them. It's all influenced by context and history and my other students and so on. I'll just leave that implicit. This is the work is directly work with them. I guess I want to say as prefatory remark for my talk that I'm going to give you citations for papers, and the full comparisons with related works, all the appropriate citations of related papers, discussion and so on is to be found there. And wasn't planning to spend talk time going through that. And I will allude to, of course, important reference points, but you should see the references there. And let me just thank the NSF and the AFOSR for supporting this work as indicated here. So that's good, especially Tristan Yen, who is my program manager at AFOSR. Okay, so let's get started. So the thing that I want to talk about is the most mundane thing you could ever imagine, which is the distinction between compile time and runtime in programming languages, which is rather familiar. We usually describe them as, two different phases of processing. That's where the phasing comes in, and you're supposed to think of, compile time as sort of parsing, type checking, compilation. I will describe it as the static aspect of the static phase, and runtime, which may include compilation if you're like a JIT sort of person. So I'm not really being finicky about those kind of boundaries, but however it is that you come about to execute it, including having the effects on people, which is the whole point of running the code in the first place. So we will have, so that's the standard thing that I'll refer to. And I guess I'm going to give this a little bit of substance based on some work going back to the late 80s or the early 90s, and then which we have been developing here in recent work that I'll describe. So I guess it goes without saying that this sort of distinction is fundamental to at least conventional widespread computing practices. I don't think I need to amplify that, but it's the foundation for all sorts of things like separate development and a particular stability under change, which I highlight because one of the bits of work I'll describe lends substance to what I mean by that. Okay, so that's where we're starting out. So as I remarked a moment ago, I wanted to rephrase these as being the difference between the static and dynamic phases in a programming language. And in typical programming languages, and okay, I will admit, my notion of typical programming languages like ML or Camel or Haskell or something like this, and the other languages you may know or favor are not too far from this, but the way in which I'm going to describe them is sort of the terminology that people use in that more type theoretically grounded languages. Okay, so the typical setup is that the languages are a priori segregated into having a static part where you have kinds that classify constructors. So you have to have a kind of types, and you close the kinds under various things. And in fact, it's not in the last, 10 years, that's been quite a subject of development, and particularly in Haskell world, for amplifying what kinds might be and how the constructors are, what the constructors are. But the idea is that they're all to do with the static phase of processing, even if it goes as far as some aspects of verification, it's all done at the static phase. And then the dynamic phase, again, the languages are usually structured so you have types classifying code. So you sort of have this usual split between kinds and constructors and types in code. And then what we have in the dynamic part varies widely. I'm not going to be too concerned about the particulars of that, but I just wanted to sort of establish terminology and way of thinking about it. So the thing I'll mention is that the way this will become important in the way we formulate it is the dynamic part depends on the static part, but the static depends only on the static. So the way in which we get a kind of separate development, as I alluded to earlier out of this, is that the static aspects of some piece of code, let's say a library or something, that's the only thing that's available when doing static checking of your code. On the other hand, when you run it, the full significance is always available. So this is compatible with, although it's not forced, is compatible with having compilation strategies that make use of or take advantage of type information at runtime. So I just want I'm trying to fix some ideas about where I'm heading. Now, the thing that I want to start out talking about is program modules, which is a favorite topic of mine since forever, but it's the framework for the first couple of things that I want to do. So I want to use it both to set up the some of the ideas I'm going to use, and also the second point in the talk will be based on this. So you don't really have to have a intimate familiarity with notions of program modules. I simply want to get across that they are mixed phase entities. That is, a program module consolidates both the static and dynamic parts. So if you look here, a very common example to use in talks, so it's nice and concise, is like a signature of queues, which has type components that are written there. I'm writing in an ML notation, but anyway, you can squint. And so we have a type of element and the type of the queues, and then operations that work on them. And I won't go, it's not necessary to read what's there other than to get a flavor. And then in implementation, fills in the blanks. So that's the idea. So the reason I bring this up is because unlike some accounts of where I will eventually head as data abstraction, we don't have, and once you have modules in play, you don't have a clean syntactic separation between types and kinds anymore. So in particular, if I take QL, which is a particular implementation of queues, and I refer to it, and it's been, I'll come back to this, but it has been, as the terminology goes, it has been sealed, that : with that signature. So the type T is opaque. That's what I'm doing there. Then, then when we have types like Q, the element part of QL, you going to the abstract type T part of QL, it threatens the phase distinction because you're projecting a type from an entity, a module that has both static and dynamic type components. And so the question that comes up is what then is type equality? What does it mean when I have, I don't know, QL.T and QX.T around, and are they equal, and what does it mean to be equal? And is that equality affected by the code or what? I mean, it kind of looks like it would be. So the idea is that if you want to preserve this traditional distinction between phases, you have to account for this somehow. So a long time ago, I think it might have been about 89 or 90, Maji made a suggestion, which I'm going to introduce some jargon here, which is to address this concern, what I will say analytically. That is, the phase distinction is explained by an explicit decomposition of all modules into static and dynamic parts. So in particular, at the bottom here, I show what could be described as an open module. That is, I have a transformer that takes in a queue and emits a queue. I don't know, I don't have something particular, all that interesting in mind, but I just wanted to give the flavor of, I'm looking at the maps between queues. And what happens is in that setting, this analytic setting, is you separate, so to speak, physically, you separate M into two parts, the static part and the dynamic part, and then the separation reflects the dependency that I alluded to on the previous slide. So this is a method that gets across the idea of the mixed phase dependency. And in fact, he formulated this using a convenient device, which is the total category of an index category. If I think of the types and code as living over in the kinds, which are related by constructors, then I can sum them all up, and that would be the category of modules. And then when you say that the category of modules has some structure, then it amounts to doing this separation. So this is a fine story. It is relatively limited in that it doesn't deal with all aspects of program modules, but people have developed that a little further, as I'll allude to in a minute. The other thing I want to mention, because it comes up in the technical development, is besides this question of when are types equal, which arises by looking at projections from things that have code and projecting out types, there's also a characteristic feature of ML, which I think is one of the greatest ideas ever and the most ignored ideas ever, if you ask me, in the world at large, is the idea of a coherent specification or a sharing specification, or if you will, it's a pullback of some kind. It's an equationally constrained product. And so my favorite example is a long time ago, we built network protocol stacks using these kind of techniques and modules. And so one of the things we had is a treatment of layers where we can formulate, a layer in terms of the lower layer, and it has a sharing specification. And you don't even really need to understand it. I just picked an example that I like. But the point is, what I'm doing is combining two modules, provided they cohere. Okay, so that's the idea. And from a methodological point of view, there's lots of reasons to want to do this. And let me not develop those. I have other axes to grind. But my point is, again, you have the question, what does it mean for that equation to come true? And as I say, we're being under the influence of the phase distinction. Well, this analytic approach that initiated with modular was developed by a number of authors, including myself, but many others. I would say that the culmination of this formulation is a recent work in the last few years by Dreyer, Rosberg, and Russo on a paper entitled Effing Modules. And the idea is to give an interpretation of a rich module language, that is a full-scale one, into System F using this idea of phase separation. So I encourage you to look at that. I think it's a very fine story, and you might enjoy it if you like this sort of thing. What I want to do here, however, because it's my jumping off point for some other ideas, is I want to just say, okay, here's another way of looking at the whole thing. So the perspective I want to get across without getting into details, and if you forgive me for the terminology, the way you're supposed to understand a program module, like what it is, what the module system of language is you compile it in your head, okay, down into what it really means in terms of System F. In the same way that the definition of standard ML worked, if any of you know or care about that, it's just that that was done on a rather ad hoc basis, and this is a rather systematic and theoretically well-grounded basis in a way that the first cuts that we did in the late 80s were not. So this is a different approach. I won't take a stand about better or worse, I'll just say different. And now you'll see why I use the terminology analytic, because our approach will be something called a synthetic account. And the basic idea is I'll write down a type theory in which you're supposed to think that every type is a module. So the whole way you start a programming language design is you turn everything in a way that I think commonly would be described as upside down, but I'm trying to argue right side up, which is, oh, you want to design a programming language? Good. What's your module system? And I advocate this seriously. So modules come first, and then you fill in the rest of the junk, okay? That's the pattern, okay? And so that's what I'm trying to do. So that's what the synthetic account is. And then what you do is you use a kind of declarative or propositionally based or based on an open, the idea of an open is how we isolate phases. And then we use the phase to condition what we mean by equality. So, and rather than some kind of translation, then what we're doing is some kind of synthetic formulation in which we recover the necessary things in using a particular pattern of ideas that I'm going to repeat in two different settings. And in some sense, my message is, geez, we're getting, this idea seems to have legs, and that's why I'm talking about it. So what we're going to start is then, so we're going to start with a type theory in which in your own mind, you're supposed to think that every type stands for a program module. And if you have no familiarity, just think of like that queue, or think of a mathematical structure which has a carrier and some operation. That'll serve you well enough for this purposes. So we're going to start with MacQueen, with MacQueen's idea. I don't think he quite formulated in the terminology I am, but let me just say that, which was the idea is you start with dependent type theory. I'm assuming you know this. This is my notation here. Can you see my highlight? Does that work when I highlight that? Come on. Yes, that good? Okay, good. So you can see here, that's my notation for sigma or now the terminology gets confusing. Sometimes it's called dependent product or dependent sum. And then this one's called dependent product, dependent function. Well, anyway, so the dependent analog of product and arrow, however you wish to pronounce them. And then you have a universe. So one of the crucial ingredients in what we're doing here is using a universe to stand for the core language. So that's the part where I say you fill that in to decide what your language features are. Okay, that's where that lives. And then what we do is we extend this setup with three different notions. One is probably more or less familiar, which is a lax modality account of abstraction and effects. So I'll explain what I mean by that in a minute. A modal account of the phase distinction, which I will again explain, and a notion of extension type to account for sharing. And the idea of extension type, if you happen to be familiar, is something that we developed and arose also in the Swedish work on cubical type theory. So ours and theirs has a notion of specifying a partial cube and speaking about completing it to a cube, given those constraints. You can kind of hear like, oh yeah, it's a little bit like sharing constraints if you squint enough. And so that's what I'm doing. I'm giving a partial specification of a scenario in a sense that I'll make precise in a moment. And then speaking of things that satisfy those constraints. Okay, so Good, and then I won't dwell on this now, but the treatment of polymorphism is not as they do in System F. I kind of abandoned that, and this is originally MacQueen's suggestion as well. Think of it as quantification over the universe. And by the way, okay, I'll just throw this in just for fun. I want to point out that MacQueen's paper was done in '86. There was a lot of work done in the '90s on this. I mean, SML was the first full-scale dependently typed programming language with a phase distinction, and I guess I'll just throw that in there just for fun, just to be provocative. Okay, so let's look at the structure of mod TT. So the setup is not going to look too unfamiliar to you. We just have a notion of signature inequality. We have a notion, we're distinguishing values and computations with this notation that you see here. And it's best if I just give you some examples and it will look familiar enough. I'm going to try to avoid getting bogged down in a lot of technicalities, but I have to say a few things. So this is what the structure looks like. The main thing to remark on is if you're used to type theory, this would be U is a type or U is a universe. This would be the elements of an element of the universe. The point being, the universe is a type that classifies classifiers, and that will come into play in a moment when we speak about parametricity. The diamond is the notation I'm using for the lax modality, which is dealt, as I said, dealing with sharing and with abstraction and effect, and sigma pi are as they always are. So here's what the formulation. So the architecture of the lax modality is that of having a notion of return and bind, as you find in a language like Haskell, and we have a way of encapsulating computations as values, which are written here with a curly brace. This is a kind of suspension, if you will, that says I'm distinguishing between a modular computation and that computation thought of as a value of the lax type. That's what is being expressed here. And we have the notion of return and bind. And the reason I want to mention that is because I alluded earlier that this colon greater than notation can be explained neatly in here, because in the formulation, the way I like to think of it, the purpose of, or the way we deal with abstraction in a programming language, that is imposing abstraction boundaries, which is essential for having maintainable code, is we have a notion of sealing, which is written as there, which says M is to be sealed with signature sigma, meaning nothing else can be known about it other than what is exactly stated in sigma. So what we do is we treat it as a pro forma effect. And that's the idea. Even though you're not maybe actually using any state, you might be in M, or you may not be, but you might in the future. So what you want to do is say, if you seal it, we treat it as effect. And that way, the notion of generativity, which comes up a lot in ML literature, it just is the idea that if I bind things multiply in the manner described here, then you're going to get distinct values X, and you're going to have distinct type components. Let me not dwell on that any further. I just wanted to make the point that one of the reasons for having a lax modality is to deal with abstraction, imposition of abstraction boundaries. That's the right way to say it. And so I wanted to mention that. Now, the thing that will prove useful for us throughout the rest of the talk in several different senses is the way in which we account for phases. And the way we account for phases is having some propositions or subterminals in the type theory, that these are to be thought of as modules. And I write them with a little lock, and because, well, there's supposed to be a, I'll explain why in a minute. Maybe it will be a mnemonic for you. So the idea is their first thing is to say that they're subterminals. Eventually, in the fuller development of this, which I will point you to a little bit later, these are going to correspond to opens in a sort of sheaf theoretic interpretation of the type theory. So you guys, I'm sure, would relate to that. So I'll just throw that in there. So these are mere propositions, as it were, meaning any two values of them are identified, and they have no elements. They're things you hypothesize. So the critical idea then is to introduce a notion of static equivalence of signatures, which is used to mediate type checking. So the point is, now if we go back to this idea that types or signatures can have value components in them, what the static flag or static lock does, I probably will end up saying the word lock. So what the static lock does is to say, well, you're supposed to compare these two signatures as regards their static phase behavior. So, and then naturally enough, if you want type checking to be something you do statically, then you ought to confine the equality checking for signatures to be performed or defined in terms of the static lock. Okay, so the way that works is by having of saying that the presence of the static lock induces identifications or collapses. So let me just say what this is, and then I'll give you a possibly helpful way to understand it. So the idea is, remember that we have a universe type, and we can have types which I will write tau. And if you're in static mode, as it were, if you have the static lock, then there is a distinguished element star, which we just put in there. Why? Because of the very next rule to its right over here, which says everything is conflated and is equal to star. So the idea now is if we think of the types as indices and we look at the fiber over a type, we're saying the fibers collapse. Okay, and the same thing happens at the module computation level. These are analogous because both of these involve some kind of runtime execution, and we want to suppress that for the purpose of type checking in this example as I'm developing so far. So, so that's the idea, is we throw those in. Things like nat and bool continue to be different from each other. You apply type constructors, you get all the behavior you want, but you manipulate them as full-scale structures, that is, modules of a signature, but you suppress some aspects of it. So that's the critical way to do it. That what makes it the synthetic approach as opposed to an analytic approach is this. So if we, okay, so that's a critical idea, and I'm going to come back to that in a minute because they will induce some modalities that I wish to explain to you. Okay, but before we do that, one reason to introduce the static lock was on the previous slide. It tells us how we constrain type checking. So that answers the first question I raised. And the way we deal with the sharing specification is through what is called the static extent. And so the idea is that we have a signature, which is displayed here, which is all the modules of signature sigma whose static component is equal to the value v. That's the way to think about it. So under the influence of the static lock, they're equal to v, meaning I'm disregarding anything that isn't to do with the static aspect of the module. And that's what this signature classifies. So in particular, if I want to inhabit it, I have to be a module of that signature, and under the lock, I have to be equal to v. That's static equivalence is exactly what's being done here. And then you recover that information on the way out. So using this in a way that I will not elaborate, you could easily imagine, I can encode SML style sharing constraints are encodable in this kind of using this kind of a type constructor. And this is the thing that generalizes the types that we've used in cubical type theory to represent partial configuration. Instead of having one lock, you can have, like in our case, Cartesian case, you can say x equals 0, the left-hand face is equal to something, the right-hand face is equal to something, and otherwise you're supposed to compose up a cube that is consistent with that. So that's the analogy, and that's where it comes from. Okay, so the next thing that's going to be used throughout, and I'm motivating it here in terms of program modules because I find it more accessible, but I'm not really going to use it very heavily in program modules, but I want to broach the idea because it makes it a little smoother, I hope, later on when I need these, when I use these ideas a little more heavily. So the first thing to say is that the static open that I described, the static lock, whatever the terminology, induces open and closed modalities, which correspond to a module being purely static or purely dynamic. And so the idea is that purely static, the open modality, that doesn't quite sweep out only the part I wanted to point to. Let's see if I can manage with this spotlight thing. So here, so the idea is I'm saying, confine yourself to the static components of sigma. That didn't behave the way I wanted it to. So let's see if I can manage that. What did I do under spotlight? It was supposed to be a vanishing pen. Okay, so that's supposed to vanish, and it's defined. Yeah, that was what I intended to do. Pardon me. So the idea is that this modality is defined just by implication or function, just as under the aegis of the static lock be sigma. So what it means is you're disregarding all of the dynamic components. And a kind of dual is not complementary in the sense of like Boolean logic, but the kind of dual or complement of it is this closed modality, which is defined as a disjunction, the push out of projections. And the important point about what happens with this disjunction is that the static component has been trivialized, which is being expressed here. So we know the static component is trivialized. And so what it means is that if you map out of this guy, you can't take advantage of any of the static components. That's the idea. They've been obliterated. So if you think of this, yeah, so that's the way to think about these two modalities. So if we think about in terms of kind of the fibers over a type, then the static aspect just looks at the base of the static only part of the types and constructors. That would correspond to the kinds and constructors we had earlier. And the dynamic part are just the fibers. And what the closed thing does is give you a single fiber in which everything has been made to be dynamic so that it's hidden from any clients in static mode. That's the idea. And if you like to think in terms of implementation, that method is consistent with the idea that at runtime, you may want and need access to the static component of the module. Okay, so I'll leave it at that. Okay, so those are two things. Now, in the present context, at the moment with modules, I'm not going to need that, but it's good to broach it. Okay, now that was like a really regrettable thing that I did. I wonder if there must be an undo. There's an undo. Good. All right. Thanks for that. Otherwise, we'd have that distraction all the way. Okay, so that's what I want to say about program modules. And my motivational remarks said, well, what I'm interested in is type identity, and I'm also interested in the nature of abstraction. So what I want to do is to outline for you the way in which we formulate Reynolds's theory of parametricity for program modules. So we have written a paper. I'll give you a reference to that shortly. That is based on as a generalization of Reynolds's theory, and I'll explain that by first explaining in a summary way what Reynolds's theory is all about. So quite some time ago, I guess it was in the 80s, Reynolds introduced this a formalization or a mathematical account of Strachey's informal idea of parametricity as a way of explaining data abstraction. And the critical idea, if I can just say it in a simple way, is you have a division between implementers and clients, and the implementers provide the type in its implementation. So I gave you some QL thing, which you probably ignored, but anyway, it was telling you how to implement the Q. It doesn't matter like what was going on there. But the important thing in Reynolds's framework in particular is data abstraction, as he was arguing, is tied up with polymorphism because the clients are polymorphic in the abstract type. So that's what is happening there. So why is that so important that they're polymorphic? Well, that's where the parametricity theorem comes in. So if you have never seen this before, I'm trying to explain to you why you make a theorem about polymorphic types in order to explain data abstraction. Okay, so a consequence of the parametricity theorem, I didn't state the theorem in its full glory because it would be hard to read. It just says if you have something of polymorphic type, and Reynolds had invented what is now called usually System F, he calls it polymorphic lambda calculus, separately from Girard, and more or less around the same time, I think. It says if you have a polymorphic expression, think about it of a client, then I get to do the following cool trick. I can interpret types as binary heterogeneous relation, meaning they relate things of disparate type. And what I have in mind here is that T is supposed to be, I'm supposed to be having two implementations, let's say of a Q, and I want to show that they're interchangeable. And so what I do is I say, well, let's consider the type implementing one Q to be equal to the type implementing the other Q, the other implementation, which is a stretch of terminology. So you can say they correspond in the way the notation here suggests. And then the important thing is, given that the client is polymorphic, if you run with one implementation and run the same code with the other implementation, you'll get the same answer relative to that correspondence. So that's the general flavor of it. I should really write there. I might have been a little bit more helpful. You must show that the operations as implemented preserve this correspondence in the sense that I will describe momentarily. But this is the gist of it, and that's the connection between data abstraction and polymorphism. Okay, so that's the idea. And from a certain perspective, we can see what John did. I don't actually know whether he was influenced by this or not. Perhaps Dana does. I can ask him later. But it's an instance. It can also be seen as an instance of Tate computability. So in the late 60s, Tate made this really clever idea, which we now call by his name. And he was working with predicates, and he was working with simply typed lambda calculus, and so it was a little bit different, but you can see this as a binary heterogeneous development of tape computability. Okay, so that's what John was doing. Now, in our setting, we're going to account for this. We're going to account for this in a slightly different way, because now I'm going to bring you back around to the terminology I said earlier. If I want to think of John as having provided some account of modularity in the sense that I was suggesting to you, then it would be an analytic account, okay, in which we boil everything down to system F as in effing modules. And okay, the advantage of effing modules is you appeal to Reynolds' theorem, basically, almost literally on the nose. And so that's kind of good. But anyway, let us just say the way that Reynolds worked, and I alluded to earlier, is treating the function types a la Tate. That is, you have a relational action of the type constructors, which basically says, well, what does it mean for two functions to be related? Well, it means it takes related arguments to related results. And then John, because he was working in, well, as we call it now, system F, had to deal with this impredicative quantification. And for this, the way you do it, at least these days, is by quantifying over a class of admissible types, which is essentially Girard's method, for those of you who know that. So it's basically a combination of Tate's method and Girard's method is the way I would see it. Now, famously, John actually worked over a set theoretic model of system F, which turned out not to exist. And there's a story about all of that. And I don't want to bring that out. I just want to allude to and jog your memory about it. Okay, so what we're going to do is we want to extend Reynolds's theory to account for the particular challenges posed by the type theory mod TT. So one thing that happens is, if you notice with system F, you have quantification over types. That is, you can take types as inputs, but you can't compute them as outputs. But I bloody well can do that. The functor thing I was showing you, or the map between queues, is taking the type part of something and computing a type as output. And in system F, there's no place to put that guy. There's no way to take in something with values and types and emit a type. So that's like a different kind of animal. The analytic account will make sense of all this by a kind of continuation passing. Anyway, let me just go on the basis that I am, because, well, anyway, that's what I wish to explain. So this is what's happening there. And then we have to deal with mixed phase dependent types, extent types, and the modality. So what we're going to do to handle this is we generalize the relational setup that John used, or it's sometimes even called relational parametricity. We're going to generalize that from parametricity relation to parametricity structures. And the reason is that we need proof relevance. That's one aspect of it. Why do we need proof relevance? Well, as I alluded to before, the tricky thing about a universe is it classifies the classifiers. And so it's not merely a property of the universe that its elements be computable or parametric, but it must carry data about why their elements are computable or parametric, as the terminology goes. So that's one thing. They're binary heterogeneous, as in Reynolds, and they're phase separated in two distinct senses. So the development I'm going to outline here again brings back this notion of the phase distinction, but in this case, it's in the context of the distinction between syntax and semantics. So that brings me to the next point. So what we're doing is we're giving a synthetic account of parametricity. We have a type theory called param-TT. And again, because of this synthetic perspective, your intuition is supposed to be that every type that I'm mentioning now in param-TT in this context is supposed to be thought of as a parametricity structure, which has two phase distinctions. It has the static and dynamic phase distinction I alluded to earlier, and another phase distinction between syntax and semantics. The idea being is that you can think of computability for types to consist of a syntactic type together with the definition of what computability is, and for that type, and I'll show you how that works in a minute. So there's going to be a phase distinction between syntax and semantics, and I'm going to say in a moment this reflects a construction called gluing, which is used to actually construct an interpretation of param-TT, but the gluing has the same flavor. The point here is that the structure of the gluing has the same flavor. The distinction between syntax and semantic, the semantic being over the syntax, is exactly the same as the dynamics being over the statics. And moreover, we're using both of those ideas in the same simultaneously in this account. So we have a syntactic phase. So we have a lock lock sub syn. And I admit, because it happens to me also, you're gonna like get confused about lock stat and lock syn. I haven't figured out a way to avoid that. I might even have typos, and if I do, I apologize. But anyway, we have a lock called the syntactic lock. And again, we have the purely syntactic mode corresponding to the purely static mode. You see, I trip over it. Purely static mode and modules, and the purely semantic mode, which corresponds to the purely dynamic mode in the case of modules. And moreover, in order to handle the binary parts of parametricity, we use a trick that Phil Wadler used of binarizing implicitly. And I won't go into any details about that, but the idea is that the static lock splits into a disjunction of non-intersecting left and right components. So that way, implicitly, when I speak of the static phase, I'm implicitly saying that it has a left and a right side, that there's two, it's all doubled up. But I'm going to the locks help me suppress that. Okay, so it's there's a kind of notational simplicity, perhaps, that comes with formulating things in the way I'm doing, and I will tour you through that now. So the idea then is what we're going to do is remember that Parametricity is a type theory whose types are to be thought as parametricity structures, which have, as I say, the structure I mentioned earlier. So, for example, a signature is interpreted as a syntactic signature together with a parametricity structure for its elements. And how do we say that? Well, we say we have this, sig is going to be an element of the universe, and I'm suppressing universe levels here. They can all be worked out. There's like 3 universe levels you need to do the construction. I'm just writing U in every case. Okay, but it all will be sorted out. And the idea is that syntactically, it corresponds, and I write in yellow, a syntactic signature, so that hopefully that will help you keep your bearings. And so the idea is that you can think of this as the collection of syntactic signatures equipped with a notion of computability for them. Okay, and then when I speak of the modules, if I look at the modules of a signature, then the modules of a signature are syntactically given by the modules of that signature syntactically. And the interpretation of this is that given a syntactic signature and its computability, I will extract its computability or its parametricity structure that corresponds to it. So that's the flavor. So they all have this syntactic and semantic flavor, and I'm getting the syntactic part of it. Then a convenience here is that we get to use universal properties of the Parametricity. Being a dependent type theory of a certain kind, it automatically comes equipped with sigmas and pi's, and I use those in a way that can almost be too slick, because you wonder what exactly is going on here. But let me just give you a flavor, which is to say that if I have a signature and a family of signatures indexed by the first one, then I can speak of forming the syntactic pi out of the syntactic components of the assumptions here, because these are parametricity structures that have both a syntactic and a semantic component. And then, so that's what I can form there. And then I can say, well, so then the semantics of the pi signature is a type which agrees with which is syntactically is the modules of sig pi, as I've written it down here. And then this is the slick part. It's interpreted exactly as the dependent function space. So this is analogous to the trick in Tate's method of saying the relation at tau1 or tau2 is the function space of the relations, as I mentioned earlier. And this is being done in dependent type theory. So that's the difference of what is happening here. So it's the same sort of flavor. Now, if we look at the core language types, then what we're going to get is here's where the idea of proof relevance comes in. So what we're going to do is we're going to say, well, what is the universe of types interpreted as? Well, its syntactic part is the syntactic universe of type, and then we have a description of its semantic part. And the point of the semantic part is we don't merely have a property of those types, but we have a structure. So we say, with each type tau, we associate it with a structure whose syntactic part, that is, it governs the values of that type tau. So that's what is meant by this extent type. And it's going to be, now this notation says, I want a type which is statically closed. In other words, that it is purely dynamic. So this corresponds to the idea that the universe types are classifying the stuff that actually runs that you kind of care about in your code, and that's the dynamic components of it. So the idea is that the elements of the universe are to be considered only as regards their dynamic behavior. They don't have static components. So that's what is being captured here. And then you do a similar trick to what I said before. If I look at the values of a type, well, a type here is a pair consisting of a syntactic type. So it's the elements that it things that it classifies are the values of that type syntactically, and it's given by tau star, which is the parametricity structure that was given there. So to take a concrete example, I'll show you which is the Booleans, which are the observables. Then what we do is we decide that the semantics of the Booleans is a type which agrees syntactically with the Boolean. So it's a parametricity structure, which explains, which is expressing the idea of parametricity, binary parametricity for the Booleans. And it's doing this by saying, well, it's a collection of bits that are essentially isomorphic to the syntactic bits, true and false. That is, it's a B star. This is a parametricity structure. It contains of something of type 1 plus 1 or 2. In other words, it's either 0 or 1, if you'd like to say. And then in each case correspond to being true or false. And the reason for these closed locks here, or closed modalities here, is to put it in the appropriate part. We're looking at the semantic part of the parametricity structure. We want to eliminate any syntactic part, and we're looking at the dynamic part because we're giving the interpretation of a core language type, an element of the universe, which itself classifies only dynamic behavior. Okay, so that's the kind of flavor of it. And the thing that I'm supposed to get across here, I'm trying to get across here is what I meant, is that by working in this type theory param-TT, I'm able to give full expression to the idea that, well, the way you do logical relations is you say every type constructor has an action on relations. So instead of doing it on relations, I'm doing it on these parametricity structures, because that gives me a way of accounting for the universe, which gives me a way of accounting for all the things I've described earlier. So that's the high level picture. And then the point is it's being presented in this manner, this synthetic manner that I have alluded to a couple of times. I'll just mention in passing, and for those of you who might be interested, I could also isolate propositional parametricity structures and treat the universe exactly as Reynolds did, but there's not too much point once you're in the larger context. So let me just leave that aside. That's a remark for people who might be especially interested in the particulars here of what is going on. Okay, so what this does for us then is gives us the machinery we need. This gives us the analog of Reynolds's parametricity theorem, which then gives us, as described in the paper, a way of saying that abstract types really are abstract in the sense that no client can tell them apart. So that's the setup. So the message then is we have a theory now of parametricity for program modules of a rather rich kind that includes sharing specifications and dependent types and so on. So in that regard, it's an extension of Reynolds' thing. Carl Crary did an analytic account of this a couple of years ago at Popple, and I would also refer you to that for the analytic side. So to a degree, we're saying this is a way of looking at things. I'm going to try to argue, though, that this way of looking at things does have legs. And so one thing that I will remark is that to structure the argument here, we made use of the exact same idea that we use for structuring module, namely this idea of an open. So we have a static open, we have a syntactic open, and then we use that same architecture to express a kind of two-dimensional structure of parametricity structure of being vertically static and dynamic, and horizontally being syntactic and semantic. Okay, that's the point of doing it. So I will then give you, I want to point you now for, if you want to understand this really in detail. So the param-TT is actually the internal language of a certain pre-sheaf topos. So you'll be interested in that. And as I mentioned before, the syntactic and semantic distinction corresponds to the gluing construction. And the static phase distinction corresponds to working with what are called phase separated sets, which are arrows basically in the category. So what is being done here is there's an arena of phase separated sets, and then you're doing gluing in that setting. And that's how you get both of those phase distinctions. So all of this work is based on my co-author, John Sterling, if I may say, brilliant PhD thesis, which he completed in October, and which he developed something called synthetic tape computability. I'll give you a reference on the next slide, which, well, as you can see, the way I presented it, it has this structure, and it gives you this synthetic formulation of proof-relevant logical predicates in his setting. And the principal application there is the tour de force application is showing normalization and therefore decidability of type checking for Cartesian cubical type theory. It's a bear to actually do this. And John developed the STC, as we call it, in order to address that problem. And then we're inspired by that to these other directions, which I'm outlining for you. So for further reading, this paper has appeared in JCM in October. It was there's a backstory on that I won't repeat, but anyway, we got it rejected at Popple, and then we turned it around and I can't resist, and then got it into JCM in a matter of months. So it was rather nice. So you can look at JCM and on logical relations as types, that paper, and I really strongly encourage to look at John's dissertation called First Steps in Synthetic Tape Computability. One might say that the JCM paper is a second step in synthetic tape computability, and I'm going to show you a third one. Okay, so we're kind of rolling in this direction, and that's what I want to show you. Okay, so that's enough about parametricity. Now what I want to do is I want to explain to you, I think I'm running along, I want to explain to you about cost and behavior in type theory. So this is a thing that has interested me for a long time because, well, I guess I think of myself as a computer scientist, and if you're a computer scientist and you're working with type theories and type theory classified programs, what's really neat is that type theory is a nice way to talk about behavior of programs. For example, merge sort and insertion sort are equal as functions on the integers, on sequences, because they both sort. So extensionally, those guys are equal. So type theory is really good at that. We have like no difficulties with that. On the other hand, I also want to say that insert sort is quadratic and merge sort is n log n. But it's a little bit of a bind, because how am I supposed to say that equal things have different properties? Like that, something is wrong here, and that's true. And so what we did is we realized we could use the phase distinction to distinguish the intentional from the extensional. And this gives us a type theory in which I can state and verify not only behavior, but cost properties of programs. And this tickles me. I have to say I'm quite fond of this. So let me explain briefly what we're doing here. I cannot go into as many details as I thought I might. Critical first step, chapeau, appropriate to use the French. Chapeau to Pedro and Tabarot. They're developing something called dependent call by push value, and therefore also a hat tip to Paul Levy for call by push value in the first place, without which not. So we're basing our work on Pedro and Tabarot's dependent call by push value because it accounts for effects. And what is the effect in the dependent type setting? And what is the effect that we're interested in? Counting the steps for resource usage. So what we do is we introduce what's called an extensional lock, similar to the lock that I described to you earlier, in which we can say, as I said before, that in the absence of lock, that's what I'm indicating here, that is in intentional mode, insert sort is quadratic, merge sort is n log n, and in extensional mode, which corresponds to syntactic or static in the other, syntactic or static in the other setting, they're equal like that. So in other words, the intentional mode codifies algorithms and the extensional mode codifies functions. Yay, like I'm really very pleased about this. I think it's a very nice thing to do. So how do we do this? Well, I'll give you an overview. So what we do is there's a primitive added to the language called stepping, as you can imagine, which is basically implemented using a writer monad, if you want to know. So there's an underlying counting. It's exactly what you think. And under the extensional modality, it's a no-op. So under the extensional modality, step of V is equal to E. So therefore, when I'm comparing merge sort and insert sort, which are instrumented in a way in which I'll describe, the instrumentation goes away and they are indeed extensionally equal. And yet I can also reason about their cost behavior in a manner I will sketch momentarily. Now, an interesting thing about this is that the step counting has no intrinsic meaning you just decide to do what you want. So with sorting, people count the number of comparisons. With GCD, you count the number of moduli. With some graph algorithm, you count the number of edge inserts or whatever it may be. So I want to promote this as a bug, as a feature, not a bug. However, it can also be related, we think, to runtime wall clock time, if you will. And we're developing a realizability interpretation to justify that, but let me just leave that aside. Okay, so we've done a bunch of things here, and I guess I don't want to, I'm going to omit this about the open and closed modalities. The flavor I want to give you is that the way you reason about cost is by doing kind of equational reasoning about steps. So for example, if I'm binding a computation that starts out with a step, I can factor the step out. And if you're not familiar with call by push value, this one might look weird to you, but if you are familiar with it, you know. So in call by push value, the function type, the negative type, is a computation type. The lambdas are not values, they're things you're going to apply. So if I think of this lambda as something that inevitably has to be applied if it's used at all, then a step on the inside can be factored out of the step of the lambda, because after all, the very next thing I'm going to do is apply it, and it amounts to the same thing. However, this is useful for the way in which we do verification. So we also do parallelism, and I don't have time to explain that, by adding a kind of multiplicative as well as additive structure, and that accounts for the span in the manner of Kuiper-Bloch, but I'm sorry, I don't have time to explain that. Okay, so now I can go back to what it means to have a cost, okay, and the idea is I can simply say what it means for a computation of type B to have a cost is E of to have a cost given by C is it's an element of B such that I can say that it's equal to step to the C of return of B. In other words, the algorithm eventually, I can, by suitable manipulation, say that it took C steps in order to return that value. So this is the cost of a computation. Therefore, I can explain what I used earlier about merge sort and insertion sort being quadratic or n log n. I can just explain that by saying that means I have a function from A to B, and for every argument, somehow I missed that out here. I have I think I have something wrong, dated wrong here, but there's supposed to be a pi a. In other words, for every argument, f of a has cost c of a. That's the meaning, as you could easily imagine.
Bob,
I guess I'm not going, yes, go ahead.
we're
You're
just
going to interrupt me. Okay. Yep. I understand. Okay. Yep, good. Okay. All right, so now I will close. Okay, I will close up. I apologize for running long. Okay, excuse me. So let me just pass over this. What I will simply say is, to define algorithms, efficient algorithms, you can't use merely like primitive recursion. You won't get the right algorithm. So we have to have a way of dealing with other patterns of recursion. And in purely behavioral type theory, this is awkward, but here it's a natural because we're doing cost analysis. Okay, I'm afraid I'm not going to be able to explain that, so you can look at my slides later on. But there's a nice closed world phenomenon about having both the intentional and the extensional aspect of a program available to you simultaneously. That's a really, there's a synergy here that happens. Okay, so I'll close by saying, for background, we have a forthcoming Popple paper that's cited here, and there's a full mechanization in AGDA, which is cited here, and watch out for UA News PhD, which will probably be coming out 2023. And then to close, I'll say, we're looking at other phase distinctions as well. For example, information flow security is naturally phrased in terms of a phase distinction. In fact, a complete lattice of phases, not complete, but a lattice of phases. That is, I can have additional structure besides a single phase distinction. We have a complete lattice of phases. And I keep saying that word. You know what I mean? A lattice of phases. And then we've also messed around with some ideas about profiling and tracing and debugging and how they can be expressed using a phase distinction. You might have a look at that. So we sort of feel like there's a bunch of things going on. It's rather nice that we're having fun with. Okay, so that finishes what I want to say. I apologize for the rush at the end and overtime. Thank you very much for listening.
Thanks, Bob. Okay, so we have time for questions. If anybody wants to raise their hand, call on people, or you're welcome to actually just unmute if you prefer.
I have a question. Can Bob hear me?
Yes, it's echoey, so I'll ask David to repeat it for me, but go ahead.
When you formulated those complexity calculations, can you also do theorems of saying, okay, it had n squared complexity, but it doesn't have anything lower? Can you do that extra part of making strict assessment of complexity?
Yeah, well, we've done a lot of exercises, particularly in the parallel case, of trying to get the best known bounds. And I don't have time to go through that with you, but there are methods of doing merge sort in parallel that we've studied actually rather closely. I mean, but we're not in the business of proving lower bounds. I don't want to say that. I mean, you can guess that we have zero to say about lower bounds, but we can have a type theory in which I can talk about the complexity.
Great, thanks. Looks like David has a question.
Hi, Bob. Thanks. That's very cool.
Hi.
I'm just wondering how you implement those synthetic art. So I guess it went by very fast for me. So the lock propositions.
Sorry about that.
Are those like built into the type theory, or are you sort of just postulating these these propositions and then working from there?
Well, I'm not exactly sure the distinction, but the idea is we formulate a type theory. So in the case of modules, we have signatures that kind of look familiar, but we also have amongst the signatures is a particular one called the static lock. Okay. And then this is carried over into parametricity. You could say I'm making matters worse. And then the justification for that is in John's work on the sheaf theoretic interpretation of parametricity. And so there they correspond to opens, and that's the way it ultimately is justified.
Okay.
So
thanks.
open being subterminal sheaves in the setting.
Judgment structure of the type, just to be clear, you don't change the judgment structure of the type theory to account for these. They're just primitive signatures.
They're primitive signatures, and when they're present, we obliterate. In the case of modules, we obliterate the runtime part. In the case of the cost, what we do is we're looking at only the behavior as opposed to the cost. And I wasn't able to explain to you another property of this type theory. We also use the closed modality to ensure that the behavior of the code cannot depend on the tick count. Okay, because you might imagine, well, I'm keeping the step counter. How come I can't write my code as if step equals 10, then do one thing, if it's 11, do another? Well, that's to do with the closed modality. I didn't have time to explain that.
Great, thanks.
So there's a question that Jacques Correct, but I'll ask a question first and then I'll read that one. Can you say a little bit about what the site of the pre-sheaf topos is, what the category is, and from that point of view, what any of the given lock modalities look like as a subterminal? Yeah,
I'm going to defer you to John for this and look in the paper because I think I'm going to get it wrong. So
no problem.
He's the expert on the sheaf theory.
Okay, and the second question, you'll probably also maybe not be a good question for the same reason, but so often when you look at a subterminal object, there's three interesting modalities. There's the open, the closed, and the quasi-closed. And the quasi-closed is kind of like not. Have you, it's the one, so you had lock implies blah, lock or blah,
yep.
And the third one is
right.
Law implies lock, right? So have you, just kind of curious whether you've looked at that third modality in any of these cases?
It hasn't come up in in the work that I'm describing here. So what I'll do is I'll ask around and see what and get back to you.
Okay, sounds great. So I think I'll read this chat from Jacques. So he says, I don't know if it's a question or not. Maybe it's just a comment. Oh, okay. Well, I'll raise the comment and you can tell me if you have anything to say about it. So phases are also quite important in metaprogramming. Being able to mix intentional and extensional is really nice. That's the key to doing static simplification of code via doing analysis of extensional properties and reflecting them to earlier stages. So if you have do you have anything to say about that or how it's relevant or how you might tie it?
It sounds right to me. But what I'm not certain about is like exactly a situation where intentional is intentional enough so that you can actually like look at the syntax of something and say, oh, is this an application or things like that, which is maybe what I'm interpreting his remark to mean. He'll jump in if that's wrong. But it's definitely very plausible to me. And a long time ago, one of Constable's early type theories called PLCB3 was of this flavor, and it might be worth revisiting from the point of view of the phase distinction. So I'd be interested to know about that. So this could be possible. The other thing I'll mention is Lakata and oh, he's going to kill me. I'm blanking on the name at the moment. Greek fellow who's now in the UK. Excuse me for the name blank. We're also looking at cost and type theory, and the way they did it was slightly different. It's kind of the exact opposite of us. I was working in extensional type theory, then using a modality, perhaps of the kind that Jacques is alluding to. This is why I mentioned it, to suppress the equations that are already present. So what we do is the opposite. We start intentionally, as it were, and then we get behavior by suppressing the stepping, excuse me. And I don't know if that means anything to someone, but it seems germane might be germane also to Jacques' comment. I'm not sure which way to interpret.
So are you saying that when you run the programs, you just like invoke the lock modality so you can't see the step counting and stuff like that?
The running part, this is just in algebraic theory. So the running is metaphorical, and the realizability interpretation is what will give us an operational semantics. But then the idea is that, the static mode stuff is what's relevant. Excuse me, the dynamic mode stuff is what is relevant. And that's what I was saying earlier, is that the true module contains the static part as well as the dynamic part, and that's part of what you run. And we're trying to develop that. I put that in parentheses. That's just ongoing work. So, yeah.
Okay. Are there any more questions anywhere in real or Zoom space? If not, we have a break, and then Brendan will give some last 15 minutes or so of remarks about kind of where Topos is and where we're going and stuff like that in the colloquium. And so any more questions before we take a break? Okay, so
thanks for coming, Dana. Thanks for coming, Dana.
Yeah, Dana was very much a part of putting this, of having you speak here. So anyway, so yeah, let's take a break, and we'll see everyone in 15 minutes. Or sorry, at 1/4 past, my fault. So 9 minutes actually. Okay, thanks again, Bob. Let's thank Bob again.
Thank you.